Yeah.
Hello everyone. I'm going to talk about our new method to analyze MIDI-infrared interferometric data, which we use to search for companions around young stars. I think you know very well that in recent years, we are able to observe fine structures in circumstellar environments of young stars. For example, rings, spiral arms, and point sources. These are several examples. Here I will focus on this question. Could we possibly detect such companions with MIDI-infrared interferometry? So let's think about such a system. We have a young star with a circumplanetary disk and a companion. If we put such an object at 150 PC and observe it with VLTI MIDI, what will we get? So the correlated flux would be like this, which means the effect of the companion would be adding a sinusoidal ripple to the correlated spectrum. So if the contribute of the primary system is a smooth curve, then the ripple is easy to recognize. However, for M-band interferometry, such ripple signals are hard to detect due to the silicate features. So for the system we mentioned above, we computed its correlated spectrum at a baseline of 50 meters. We get this. So you can see the strong silicate feature here, but can you see that there's a ripple here? Maybe not, but actually it is there. So this overall correlated spectra is a sum of these two parts. So the contribution from the primary system, which has a silicate feature, and a weak ripple signal caused by the companion. I enlarged it. So the ripple signal is hidden in this spectrum. And now the question is, how can we disentangle these two parts? So the method we propose is this. We could compare the shape of the multiple correlated spectra taken for one object. So if the baseline lengths are not too different from each other, then the silicate feature from the primary is expected to have a similar shape, like this. On the other hand, the ripple term can be very different from each other because even a small change in baseline length or a change in position angle of the baseline could shift the position of the peaks. Therefore, if we see the change of the shape is likely to be related to companion. So in order to quantify the difference in the shape, we use the following algorithm. So for each spectra of the three, we first subtract the continuum so that we subtract the continuum so that only the feature is left. Then we normalize it so that the peak is always 1. Then now we have this shape of the feature. Then we can find what we call differential spectrum. It's defined as each spectrum minus the average shape. So we have this differential spectrum. So for the binary system we mentioned above, we get this differential spectrum. And if we remove the companion and have only the star disk system, then the shape of this correlated spectra are very similar to each other, like this, and the differential spectra is almost zero. This means when we observe this kind of differential spectrum, we can know that such a signal comes from companion. Okay, activities in the above, we assume homogeneous dust mineralogy. In reality, spatially varying mineralogy is possible around young stars. For example, for this several Herbig star, they have crystal silicate in their inner region, but have amorphous silicate in the outer region. So therefore, we also simulated disks considering such effects. For such a model, we expect the silicate shape, even without companion, should change with the baseline length. However, if we choose baseline length within a narrow range, then this effect would still be weak, as shown here. Therefore, when we observe such a differential spectrum, we can still know that it's related to companion. In summary, with this method, it is possible to detect faint companion around young stars with a flux ratio of only 0%. We are already applying this method to MIDI archival data, and we seem to have some interesting preliminary results, but we need some more check and confirmation. Hopefully, some more results will soon come out. Thank you.
Thank you very much, Lai. There are no raised hands yet. Also, I don't see any questions in the exoplanet channel yet. However, I did have a question myself, and this concerns, so you are basing now this analysis on looking at the correlated fluxes. I was wondering whether the phases would be a more sensitive diagnostic. So either in some way, perhaps using the differential phases that you can measure with MIDI, but of course, in a much better way, you might be able to use the phases measured with Matisse for future observations.
But if the flux ratio is only several percent, then it also means that the differential phase would at most be the same number. If the flux ratio is 1%, for example, then the differential phase is no more than 0.01 radian, which is less than 1 degree. So it would be hard to measure.
Yeah. I guess perhaps in L-band it would be possible, but it would depend, of course, on the SCD of the companion, how bright it is at L-band.
But if this companion are generally redder than the primary, then in L-band it tends to have even lower flux ratio. I think that's the challenge.